Hello. So today we are going to be talking about glycolysis and gluconeogenesis pathways. Okay, so we're going to start with glycolysis phase 1. As you can see in the diagram to the left, it is all phase 1. And there's a priming reaction that must occur, which is the first step where hexokinase, the enzyme that's going to break down ATP and take one phosphate and give it to the glucose 6-phosphate. And then from that glucose 6-phosphate, it is going to be phosphorylated and take from D-glucose 6-phosphate to D-fructose 6-phosphate. Okay, and that's done through an isomerase, another enzyme. Okay, and then we start in our second priming reaction, and that is taking the fructose 6-phosphate and making it into fructose 1,6-bisphosphate. Okay, so by that, it is going to be done through a phosphofructokinase 1, so another enzyme, and also a phosphate is taken from ATP to make ADP. Okay. All right, so now we are at fructose 1,6-bisphosphate, and we're going to be in the cleavage of that 6-carbon sugar phosphate, and it's going to be made into 2 3-carbon sugar phosphates. Okay, so it is going to be made into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. And that is all done by aldolase, another enzyme. Okay, so, and then lastly, it is step 5 down at the bottom where you can see right here, and that is where we have the 2 3-carbon sugar phosphates, and they are going to be transferred into glyceraldehyde 3-phosphate. Okay, so that's done by triose phosphate. Okay, so overall, in this phase alone, we had 5 enzymes that were used to break down each form of glucose and phosphate groups. Okay, going on to phase 2 of glycolysis. And this is where we come in from phase 1. So we have our glyceraldehyde 3-phosphate, the 2 of them, there's 2, as you can see. And now we're going to be turned into 2 1,3-bisphosphoglycerate, and that is done by another enzyme, which is dehydrogenase. Okay, so the oxidative conversion of glyceraldehyde 3-phosphate to pyruvate, and that is done through oxidation and phosphorylation. Okay, notice there's something different with the second phase of glycolysis. we have added in the 2-NAD. You can see that here. And we are going to add a hydrogen ion. So now that we have 2 NADH and 2 other hydrogen ions. Okay, so now we're going into the first of the ATP forming reaction, and that is done by taking the 1,3-bisphosphoglycerate, and we're going to kinase it with that kinase enzyme and make it into 2,3-phosphoglycerate instead of the biphospho. Okay, so it's just 2,3-phosphoglycerate. And then we took our 2-ADP and made it into 2-ATP. Okay. Next, we are going into step 8. So we have those 3-phosphoglycerate, and we're going to go through another enzyme, which is phosphoglycerate mutase. And that pretty much takes away one of our phosphorus, and then it is going into 2-phosphophenyl pyruvate, and that is done by enolase, another enzyme. Okay, so then with that, in that same reaction, we have water. 2 molecules of water were made. Okay, now we're down to our second and last step, 10, where our 2-ADP are going to be made into 2 more ATP through pyruvate kinase, and our phosphophenyl pyruvate is transferred into just 2-pyruvate through phosphorylation. Okay, so if you notice, there were 1, 2, 3, 4, 5 more enzymes on phase 2. So that is a total of 10 enzymes that were just used in glycolysis alone. And that is pretty amazing. Okay, so going on, so the main goal of glycolysis is to produce ATP. Now, mind you, that the ATP produced in glycolysis is not much. Okay, so there's not much ATP made, and that there are 2 forms of it. Okay, so we have an aerobic and an anaerobic pathway that the new pyruvate can take. So there is the anaerobic fermentation or homolactic fermentation. That's one pathway, and that's obviously going to make lactate. And then we have another one for anaerobic, which is alcoholic fermentation. Okay, so that is where carbon dioxide ethanol is made, or alcohol, and then for lactate is lactic acid. So the way I like to remember that is that when you work out, your muscles get super tired, right? And then you need all that lactic acid is building up, and then you will release it once you get more air. Okay, so we have aerobic oxidation. So then it's going to go through the citric acid cycle or Krebs cycle. Okay, so Krebs cycle is just another word for, or another name for the citric acid cycle. Okay, so then that's another 4 ATP that's made in the citric acid cycle. And then we have the oxidative phosphorylation. Now that is the electron transport chain. Okay, so ETC is where most of ATP is made, and it's about 32 to 34 molecules of ATP that are actually made. Okay, so other than ATP, carbon dioxide and water are made in the aerobic oxidation cycle or pathway. And then for each fermentation cycle, it's only 2 ATP. So no new ATP is made. The ATP that was made from just glycolysis, it's continued to be made in fermentation. Okay, so here is just a little animation to show you the transfer of the phosphates and the 3-carbon sugars and how they make the 3-carbon pyruvates. So you can see where the NAD plus is then made into NADH, so it's adding that hydrogen ion, and then ADP turns ATP. Okay. Okay, so after glycolysis, so we talked about the anaerobic conditions, both of those, and then we talked about the aerobic conditions. Okay, so a good way to remember the ethanol is you have to ferment beer, right, in order for it to taste right. So you put yeast or bread, right? You can put yeast in bread to make it rise. So what is given off when bread rises? CO2, right? Okay, so that's a good way to remember that when anaerobic fermentation is occurring and it's ethanol based, bread, beer, any type of alcohol, and that's CO2 being released. Okay, and then for the lactate or lactic acid fermentation of lactate is made by the muscles, like I said before. So it's that lactic acid buildup. And then this amount of CO2 just keeps building up because you keep working those muscles out and you're using more and more oxygen. Okay, and then for aerobic conditions, so that's mainly what's being used daily by animals, plants, and any other bacteria that go through cellular respiration. So lots of CO2 and water are being made through the aerobic conditions because we're respirating out. So that means we're getting rid of the CO2 that was produced. And then also small forms of water being released back into the air as well. All right, so now we are on to gluconeogenesis. So it is literally the glycolysis process reversed. Okay, so we're literally taking the pyruvate and going backwards. So, and that's called gluconeogenesis, right? Okay, so then as you can see in our diagram here, we have pyruvate. And then we have these double arrows. These show that it can go either way. So gluconeogenesis begins at pyruvate. Okay, so notice how we have pyruvate here, and it's going to be made back into phosphoenolpyruvate, so PEP. And that's this right here. So once it's there, it's going to require that 6 ATP are used, and then glycerol is made by glyceraldehyde. Okay, so the reason for gluconeogenesis is to decrease the level of glucose in the blood. So this is where our type 1 diabetes comes into play. So if there's too much or not enough, then the blood levels are too high, too low, and it can cause somebody to pass out or to go into shock, and we definitely don't want that to happen. So this is something in our body that automatically does it for us. So like I said before, as you can see, the different going arrows. So it means that they can just go either way. It's reversible. Okay, now for glucose, it is not a reversible pathway, but gluconeogenesis is. So keep that in mind. And protein is needed to make the amino acids. So the amino acids down here. Okay, so those are needed in order to make pyruvate. So then this whole pathway only occurs in the kidneys and the liver because of glucose. Okay. Okay, so as you can see, we have both sets of pathways here. So we have glycolysis, and then we have gluconeogenesis. So notice that only on some of them we have the double arrows. So we have double arrows, meaning that it can be reversible once again. So gluconeogenesis is going the opposite direction that glucose is going. And then we end up back at glucose. So if you look at it, it's just pretty much a giant circle, starting with glucose, going with water, and then ending back up with gluconeogenesis. So it is definitely a needed process in the blood in order to regulate blood glucose levels, and without it, we would go into diabetic shock. Okay, once again, some more differences we have here. And glycolysis converts glucose into 2-pyruvate. And we have the raw material that's used is glucose, occurs in the cytoplasm, while glyconeogenesis occurs in both mitochondria and cytoplasm. The raw materials in gluconeogenesis is lactate and amino acids, so those are needed in order to begin the process. Okay, and then produced is glucose. So instead of using glucose, it is what's being produced in gluconeogenesis. Okay, and then glycolysis is catabolic, while gluconeogenesis is anabolic, and glycolysis is exergonic, while gluconeogenesis is endergonic. Okay, and then finally, there's 10 reactions. Remember those 10 enzymes that are needed in order to keep breaking down in those phosphate groups. And then we have 2 glycolytic pathways with 4 new reactions. Okay. Okay, now some fun facts about glucose and why it's needed. So our brain needs sugar in order to function. Okay, so it uses about 20% of the energy that is produced by cellular respiration. And that is, it needs sugar in order to even begin that process. Then we have the different foods in sugar, which is not really the sugar that we need, because sucrose comes from the table sugar. Then there's maltose, which is malt sugar, which just is in its most okay, so then we also have lactose, which is the milk or the sugar that's found in milk. And then starch, which is found in all types of plants and a lot of vegetables, actually. Okay, so then we have our internal organs. So the liver can store the excess glucose as glycogen, and that is where our body fat comes from. So the more glycogen that you have is probably more fat and adipose that you have in your body. Okay, and then we have digestion. So the enzymes that break down these sugars in these foods to make the glucose that's being transported in through the blood. And then we have physical activity. So once again, our lactic acid part of glycolysis, and sugar is needed in order for energy to be created. So it's going to take that glycogen from the storage and bring it out and start making energy to keep up with whatever physical activity you're doing. Okay, so then your sugar levels are regulated, and those are through insulin and glucagon. And then the pancreas is producing enzymes that regulate this from then on. And if there is a failure in the production of insulin, then it causes type 1 diabetes. But if there's too much insulin that's being produced, then type 2 diabetes becomes an issue. And that's just having your diet is too high in sugars and or starches or certain foods that carry a lot of sugar that can cause your levels of glucose in your blood to rise to unhealthy proportions. And by not having enough glucose, then there will be an issue with the amount of energy that can be produced. Okay, then we have carbohydrate intolerance of glucose, galactose. So that's just another area where if there's an issue with carbohydrates being broken down and then glucose cannot be made because of that intolerance, and then complex carbohydrate intolerance, somewhat similar to carbohydrate intolerance of glucose galactose. Okay, and then monosaccharide malabsorption. So that is when, once again, a carbohydrate is not absorbing correctly. And so there's issues with that when it comes to glycolysis as well, because carbohydrates are used in glucose as well, other than just plain sugars like glucose. All right, so that ends the presentation on glycolysis and gluconeogenesis, and I hope all of your questions were answered with this presentation, and these are the references that I used. Thank you.